He's going to be speaking to us today about climate change and paleobiology, sort of stuff.
Yeah, sort of.
She's a scientist and she's awesome. So everybody enjoy.
All right, so like Sean said, my name is Christine, and I'm working on my master's at the University of Alabama in the Department of Geological Sciences. I'm going to switch gears entirely, and I'll preface this talk with letting you all know that I know nothing about coding. And in fact, I sent Sean an email last night saying, I don't know what type of adapter my computer needs. So this is all very interesting to me, and I'm really excited to be here. I don't get an opportunity to speak to a generalized audience very often. So I'm going to tell you a little bit about my master's research, which involves a lot of different disciplines. It involves a little bit of biology, a little bit of archaeology, and a little bit of geology. Okay? And so you may have noticed that there's an election coming up, right? And there are a lot of hot debates going on, and climate change is one of those really hot topics this year for those debates. In fact, President Obama recently visited Alaska for a conference that was discussing the impacts of climate change, where he stated that climate change is no longer a far-off problem. It's happening here, and it's happening right now. Right? And so, in fact, this is a little barrier island in the Chukchi Sea in northwest Alaska. It is called Kivalina, and its inhabitants applied this year for a grant that would fund its relocation to an entirely different place in Alaska. And Arctic environments like Kivalina are experiencing warming at twice the average rate of the rest of the world, right? And this is really important because what the result of that is that sea ice is forming later each year. And so sea ice for the inhabitants of Kivalina is a really important platform for hunting. And not only do they use that sea ice to hunt for seals and fish and sometimes whales, it protects their islands from increasingly strong winter storms, right? And the really cool thing about sea ice, as you probably know if you've read a couple of articles online, is that it's a really good indicator for what's going on with our climate today. Right? And this raises a really important question. We know that the sea ice extent is decreasing at an alarmingly fast rate. And so this is a little graphic that I pulled up from Weather Underground that shows what the sea ice extent was in 1970 and how it's decreased all the way to 2007, and then the decrease that we expect to see all the way up into 2100. And it's pretty shocking, right? And so the impacts of that are really huge, right? And one of the other questions that this raises is, well, if this is what's happening today, how does this compare to sea ice extent in the past? Because it's really important to contextualize the changes that are happening. And so as a paleoclimatologist, I'm hoping to contribute to that discussion a little bit. And so scientists who study past climate, they use, many times they use changes or signals of change in the water chemistry that are recorded in the hard parts of an organism during its life. And so shells and bones and teeth can all tell us about an organism's life history. It can tell us about the environment in which that organism was living. And many times it can tell us something about water temperature, right? And so this is a common proxy for water temperature. These are called foraminifera. These are tiny little microscopic organisms that you can't see. But they precipitate these really beautiful calcium carbonate shells. And they record the water chemistry perfectly. And so we can actually use a little bit of math and a little bit of chemistry to come up with what the sea surface temperature was, or the seawater temperature was, in which these little guys formed. It's really cool. This is no trivial task. There are a lot of complications that come up with that. And in Alaska, the complication is the runoff from glaciers and streams of fresh water. And so you get this fresh water mixing with seawater, right? And so it's really hard to get reliable temperature calculations when we don't know exactly how these two are interacting when these little organisms are forming their shells, right? So I'm working on a method that would allow us to learn something about seawater temperature without using water chemistry data. My method actually relies on the regular growth of clam shells. So what I did, I had to go to this really awful place called Kodiak Island in Alaska for 3 weeks. It was terrible, right? As you can see, I mean, you would probably hate to be there for 3 weeks. And so what I did is I collected samples of a common butter clam called Saxonomus gigantea. And this clam conveniently stops growing at a temperature right around freezing, so at a temperature where it would be sustainable, or you could sustain sea ice. Right? And so what I'm hoping to do is to measure the length of the growing season of these guys. Okay, and so when that temperature reaches freezing, so usually around wintertime, they produce these really distinct lines, right, that are visible in the cross-section of the shell. They also produce really small lines between those winter growth lines that happen at regularly known intervals. And so theoretically, I should be able to count the number of those tiny lines between the winter growth bands to know how many days that clam was growing each year. So that'll give me something about seasonality, right? So I can now know how long the summers were lasting, and then maybe I can collect shells from different locations and compare them and know something about the water temperature and say, well, hey, maybe the clams that are growing further north have a shorter growing season than the clams that are growing further south, right? Because the water will stay longer or colder longer in Alaska than it would further south. So if any of you have ever talked to anybody who's done field work, or many of you are graduate students, so you know what research is like, you mine all of the previous research to find out how previous researchers have come up with their conclusions, and you look at their methods, and well, sometimes the methods aren't really that explicit about what they actually did. And so I called up a couple of researchers who have done a lot of clamming, right? And I said, well, hey, I'm from Georgia, and I'm doing my research in Alabama. How do I find these clams on the beach, right? So I said, okay, well, here are 3 locations you can go to. You just go at low tide, and you dig a little hole in the beach, and they'll be there. So that's what I did. And I found nothing, right? So I got a couple of grants from my department. I got a grant from the Geological Society of America. And I go out 3 days looking for these things, and I find nothing. And I'm panicked, absolutely panicked, because, oh my God, I have money, and I'm here, and I'm going to go home empty-handed. What do I do? So I sent some emails to a couple of folks on the island, and I said, well, hey, you guys go clamming a lot. You're pretty familiar with the local ecology. How do I find these clams? So this is what I thought clamming looked like, but in actuality, it looks like this, right? So what we had to do is go at low tide, and it turns out you had to have a -1 foot low tide, so the tide had to recede 1 whole foot for you to find these guys. And fortunately, while I was there were a couple of -1 foot tides. Could have ended very badly, right? And so you have to take a rake, okay, and pull back the sediments. Actually, I guess I skipped the part with the shovel. First you have to break the rocks, because in Alaska the beaches are pretty much rocks. They're not sandy, they're pebbly. So you have to take a shovel and dig a hole, break back the sediments, and you have to stick your hands in there and feel around for these shells, right? And you find all sorts of other cool things while you're doing this, so of course I had to look at it. I couldn't just go for the clams. But I did find a lot of clams. I found 150 of them, right? And I was pretty excited. It was a really good day for me, until I had to go home and shuck them all. That was awful. So you can see, a lot of times as a field scientist, things don't go as planned, and you kind of have to be resourceful and figure out how to make things work, but sometimes you have success. And one of my favorite pictures from this trip, actually, Sean reminded me that there was a Twitter feed a while back that was called Field School Fails, or Fieldwork Fails. Well, this is me pointing to a spot where some random dog came up to my book bag on the beach and left his little mark on my backpack at the end of the day. Nice close up. But it was fantastic though. So right now I'm in the process of analyzing these shells. And it's a lot of work and it's a lot of fun, but the really cool thing about this is that if I'm successful, I can apply this method to ancient shells. And this provides the potential to reconstruct seasonality over the past 8,000 years in Alaska. And because these shells come from archaeological sites, we can also learn something about how humans adapt to climate change and something about human resiliency, right? And so you get to see all sorts of cool artifacts that are found in association with a lot of these clam piles and archaeological sites, right? And to go back to that resiliency is oftentimes what it means to be human. And to quote President Obama, even if we can't reverse the damage that we've already caused, we have the scientific innovation and the imagination to avoid irreparable harm, right? So with that, I'll answer any questions. I didn't really go into the methods, but if you have any questions about what I'm actually doing in a lot of sciencey jargon, I would be happy to elaborate. But are there any questions? Yes.
Okay, so you can definitely look at the past 8,000 years within Alaska. Did these shells grow in other parts of the world over the past 8,000 years so that you could actually look at data for the entire planet and have a way to compare?
Yeah, so there's actually this whole subfield of geology called paleoclimate, right? And so we have probably hundreds of different proxies for paleoclimate. So these specific clams only grow between, I'd say the state of Washington all the way out to right around the Aleutian Islands in Alaska. So we would have the potential to do that, but they aren't necessarily abundant in all of the archaeological sites throughout the Pacific Northwest, but they are definitely abundant in the sites in Alaska. So for other sites, there are definitely a lot of different proxies that you can use for sea surface temperature or for different environmental conditions, which include like corals. Those little foraminiferas are really popular. I mean, I could name proxies all day. So you typically find one and you specialize in it, and then you have to know something about water chemistry and how those shells form their shell, or how the clams form their shells, right? And the other limitation for that, though, is that you have to have a species that is still currently extant, right? Because you have to know how it grows, and you can't do that with a fossil. So you are kind of limited in your time range to really last, to what's still hanging around. I mean, there are other ways that we deal with climate questions in much older records, but what I'm doing specifically applies to the last 8,000, 12,000 years. Yes?
That was really cool, important work. Because I am a grad student, I'm curious about the methods and the boring technical terms. What do you like? You slice a shell in half and then look for those, and how do you image it, and what programs are you using? Can you use like ImageJ or?
Yeah, so what I do is I take the shell and I cut it in half, and then I actually have to run it on a little drill where I drill little holes all the way along the cross section here, right? So I'm using oxygen isotopes to tell me which are actually winter bands, because sometimes those bands actually form when you have an extreme amount of fresh water running off from the mainland, right? Sometimes they form in storm events, so I actually do have to identify which ones are winter bands by using isotopic data, right? Then what I do is I make what's called an acetate peel, where I put a little bit of acetone on my shell and a couple of other things before that, and then I put it on acetate paper. I can peel it off and then put it under a microscope and take an image. And then I use this really awful program called Windindro. So if you guys want to develop an awesome program, help me, please. So Windindro is really awesome if you're a dendrochronologist, right? But the bands on tree rings are much thicker than these guys. You can see, like, this is a 1 millimeter scale. And so I oftentimes struggle making that program recognize the scale that I'm working on, since it is designed for tree rings and not for shells, right? So that's the program that I'm using, and it does actually fairly accurately recognize these, and then it'll count them for me, and then it'll actually measure the distance between them. So it's a pretty neat program.
So to add to the list of things that you think your work lives within, I'm going to put one more there. You're doing material science work, and there are a lot of people who have developed really advanced imaging techniques to do this stuff, and I think it would be really great to find at your university or even nearby some people who are doing something like Raman spectroscopy or scanning electron microscopy, because there are people in the natural materials space that are doing stuff like this.
Yeah.
So, yeah.
So actually there's a fellow on my committee in my department who does actually do that. But what we decided is that those methods are far too complicated, and the preparation is just way too much time for what I need for this project.
Certainly.
There are definitely people who are looking at clam shells and looking on a very microscopic, like a tiny, tiny little scale of how these things are actually forming individual crystals in their shells, but it just doesn't fit into the scope of this project.
So are these optical images? Was this optical microscopy?
Yes.
Okay. So some things that I would suggest are looking at something called scikit-image. It's an open source Python library that would be able to detect some of these lines and kind of automate some of this stuff for you very nicely. And the learning curve might be a little bit high, but if you can find somebody who's acquainted with Python already, it will be a good place to start.
Sure. Awesome. Well, thank you for the suggestion. Any other questions?
You were talking about once you figure out all of these, how the humans adapted to the climatic changes, right? Mm-hmm. Would it also help in weather forecasting, like telling that, okay, this is what is going to happen in the future?
So potentially, right? So one of the things that this can help us reconstruct is sea ice extent. And so one of the things to make a good model for what's going to happen with sea ice extent and sea ice melt is knowing as much data as far back as you possibly can. So in that sense, yes, it certainly can. But this is a really new method. So this actual process is called sclerochronology, where we're using just the shells to say something throughout time, right? And we're probably, with sclerochronology, we're probably where we were with tree rings 40 years ago. So it has the potential to be a really useful proxy, but we're still learning a lot about how these shells form, right? And there are a lot of complications, and there are a lot of assumptions that we make that we're still trying to disentangle. But yeah, potentially it would be very important for making good models.
one more suggestion. This might be a little nerdy. Maybe we talk about it afterwards. But doing sample prep in the opposite direction. So you cut it at a really sharp angle, so that you're kind of like a measuring glass when you look down on it, and it's got the diagonals on it that are telling you how many ounces are there. If you were to cut that shell that way, the lines would become distinctive in another direction, and it might actually expose some more of the winter growth lines just because of cutting it at a very sharp angle.
Yeah. Well, the winter growth lines are actually really easy to see. I mean, when you cut the clam, you can see these lines.
Sure.
Without any microscope at all, but you have to be able to know whether or not they're winter growth lines or whether or not they're a result of some other environmental factor. And so we use isotopes to do that, but I mean, they're pretty easily visible.
But when you see, the thing is when they're easily visible and you have a lot of them, it makes your job harder as a scientist. If you can automate some of that process or at least filter it, you get to do more of your work, right? Because you have 150 of these things and then a bunch of microscope images from them, perhaps.
Actually, I'm only analyzing 35.
Oh.
And that is actually a valid point. This is maybe somewhere I would take this as a PhD, right? Because I've only got 2 years to do this. And most of the work similar to this, they've only used 1 or 2 shells, right? So I'm going off of studies where they have data and they're making very big statements with 2 shells worth of data, right? So 35 is still quite an undertaking, but absolutely, if I continue on for a PhD with this, that would be something that I would definitely want to look into.
And time.